1996, and that has since seen over 400 students pass through its doors. You've guided over 70 postgraduates through postgraduate research studies. You've published over 50 books, many of which are what you might call sort of leaning towards the popular science end of the spectrum, as well as highly technical research papers. And you've then published over 400 papers. You were, with a body of work like that behind you, I imagine the Royal Society were delighted to enroll you in their membership in 2014. And your research still goes on. You're going to introduce some of that tonight on the subject of tracing the color in dinosaurs. So thank you, Mike. Over to you.
Thanks very much. So thank you all very much for coming. And I'm going to tell a story that has several interwoven aspects. The main part of it, of course, is to talk about how on earth we could know the color of dinosaurs. And that links to a wider theme of scientific approaches in the earth sciences in general. Because in much of what we do, I'm a paleontologist, so I study the life of the past. But earth sciences covers geology and other fields. And many of you might think, well, we have to speculate about the life and times of the past. Whereas I will try and introduce you to the idea that there are actually, in most cases, testable methods so that we can be very sure of what we're saying, and we're offering testable hypotheses. So the question of color is couched in those terms. And it's not that I'm giving you an opinion. I will lay out the evidence, which can be challenged, of course. But thirdly, is to make you very aware of the fact that my slides will come on eventually, I hope. I'm just waffling until they eventually appear. Oh, thank you very much. That's very kind. No, that's not quite it yet. Hello, that's Ray there. Yeah, lovely. Thank you. And my third theme is to remind us how short a history we've had of these fantastic fossils from China. We're so used to these amazing things appearing, we think they've been there forever, perhaps. But in fact, when the book came out last year, that was the 25th anniversary, that's all. 25 years only of all of this amazing stuff coming out of China. So I want to go back 25 years, 1996, the meeting of the Society of Vertebrate Paleontology in New York. This is the American Museum of Natural History. And something very strange was going on. There were all the normal papers. It's about 1,000 people attend this meeting. So there were multiple meetings and sessions on all kinds of different technical aspects. But there was something going on in the corridor, which was reported in this very famous short piece in the New York Times. And the New York Times is a highly respected paper. And Malcolm Brown, a science journalist, wrote this piece during the week of the meeting, and everybody was reading it, they saw this, and people were aware that things were going on. And unusually, for a science journalist, he was not reporting one of the papers that was being given at the conference. He was reporting whispers and rumors that were going around the corridors at the time of the meeting. And I remember this strangeness about the meeting, because a small delegation of Chinese paleontologists had come. And that was very unusual at that time. And they clearly felt a little nervous wearing their black suits and not quite fitting in with all the jeans-wearing American paleontologists. And they had the most amazing photographs of fossils of a sort that nobody had ever seen, giving hints of what is mentioned here in the title. Could it be that dinosaurs had feathers? That was the big question at that point. This is a photograph of the specimen that they were showing. And the professor, one of the team, Peiji Chen, from the Nanjing Paleontology Institute, had this photograph of a fossil. And it's about 1 meter long. The tail is about 1 meter long. He didn't have the specimen, he just had the photographs. And he was saying, look at this thing, it is obviously a dinosaur, it's not a bird. Look at the length of the arms. And yet it has this fuzz of stuff all over the back and tufts along the tail. Could these be feathers? And he was showing it to all the different people at the meeting who were debating it, and everybody, all the Americans and others, they were saying, we want this thing, can we get it, and can we see it? And it wasn't then the easy thing it is now to go to China. Curiously, at the same time, October 1996, there was something else had happened. And there was only one person at the meeting who knew about both things, and that wasn't me. That was Phil Curry. I don't think his name is there. Phil Curry, the dinosaur expert from Canada. And so he was at the American meeting. He was looking at these photographs with everybody else. But he had been in Beijing the week before, and he had seen this specimen. And indeed, during his visit to Beijing, the two professors at the Geological Museum there, G and G, were ready to publish their paper. And it was published in Chinese. So this is a later English translation. But they were determined that this thing with feathers was a bird. Their logic was, it's got feathers, therefore it must be a bird. Even though it had short arms, clearly could not fly, etc., etc. And in the classification, they make it very clear, aves, birds, blah, blah, blah. And they call it Sinosauropteryx prima, which is something like Chinese reptile wing the first, something of the kind. And indeed, this is the first named feathered dinosaur from anywhere in the world, 1996. But the people at the meeting in New York were unaware of this because it was published in the Chinese language in the Journal of the National Geological Museum in Beijing. Oops, let's see if I can make this work. Ping, ping. Oops. Oh, yes, that's right. Oh, there's Ray again. Lovely, thank you. And Chen was able to publish his paper about the Nanjing specimen 2 years later. He published it in English in Nature, so it got enormous publicity. This is pretty much the #1 scientific journal in the world for everything, and it was a big splash. But he was not able to name it because it had already been named. However, maybe you noticed something. This is the Beijing specimen, the holotype, the type specimen of Sinosauropteryx prima. This is the Nanjing specimen that we were all seeing at the New York meeting. Do you notice anything about them? Bit of skullduggery. They are, in fact, both two sides of one specimen. But nobody knew that at the time. And it only became clear later. And I've asked various Chinese colleagues what was going on and who sold you these and how much did you pay? But they won't admit it because I think they paid a lot. And both institutions were ambitious and keen to, and at the time, of course, this was seen as unique. Now there are so many specimens, but obviously some smart dealer somewhere in North China got the thing and thought, you know, I could sell these, and probably got as much for each as he would have got for both sides. And these were the two premier institutions in China, and they were each buying it, thinking it was unique. Anyway, there we are. And then since then, thousands and thousands of specimens have come to light of this kind. And I just want to remind you of where we were at that point. What was the impact of this? It's not just that these are amazing fossils, but in terms of our knowledge, what did it mean? And in fact, not much had happened really since the days of Darwin and Thomas Huxley, shown here. Because the only Mesozoic fossil bird, the only fossil bird from the age of dinosaurs that was really known at that point was Archaeopteryx. And it was first found in 1861, which was perfect timing for Victorian science. Darwin's Origin of Species book had been published in 1859, and he had 2 chapters in the book about fossils. And Darwin knew about geology, he studied geology and fossils. And he argued in the book that if we could find intermediate fossils between major groups, this would be a wonderful proof of evolution. And lo and behold, 2 years later, here it is. And so this is one of several specimens of Archaeopteryx. And what Huxley saw is the skeleton of a dinosaur, and it has a long bony tail. The jaws are lined with teeth. It's not immediately a bird-like skeleton, it's a dinosaur-like skeleton, and yet it's got wings. It's got feathers, I should say. It's got feathers and sufficiently specialized that clearly it's got the complex array of feathers to form a wing. Almost certainly it could fly. This is a bird. And Huxley memorably said it was a dinosaur in bird's clothing. But by about 1990, we hadn't really got an awful lot more. We've got dinosaurs, we've got Archaeopteryx in the middle, we've got modern birds, and indeed the fossil records of modern birds had been traced back into the late Cretaceous. But there was a sort of long gap of 70 or more million years, and that was it. And so, of course, Archaeopteryx was very important because it's all we had. But also it became a kind of weakness of arguments about evolution. The creationists loved Archaeopteryx because they could say, well, look at that thing. We know nothing about the origin of birds. They just suddenly emerged like this, like a sort of miracle. It's not the kind of evolution that Darwin talked about. So there was that where knowledge was before the Chinese specimens, and they filled all the gaps. So just to give you a picture, this is one of the localities called Psittacosaurus, and I was fortunate to first go to China in 2007, and I've been many times since. And all of these fossils come from North China. This is Liaoning province, which is where many of them come from. And the Psittacosaurus locality, when we remember that there are only about 12 decent specimens of Archaeopteryx, that's all. And it was often called the $10 million fossil, you know, the most valuable fossil on Earth. This one locality produced 1,000 specimens of fossil birds of equivalent quality, each with a complete skeleton, with all the feathers and everything else. And so it just unbelievably changed our knowledge. And the specimens have come from many, many localities around China. And not just those that age in the middle of the Cretaceous, but there are localities of Jurassic age as well. And so I'm talking mainly about these Cretaceous ones, and they are part of an assemblage with a great variety of organisms. They are ancient lakes. I should say a word about this. These are sediments laid down in ancient lakes. They're very thinly bedded sequences of fine-grained mudstones and limestones. And the orange color comes from iron in the sediment, because actually a lot of that sediment is reworked water-laid ash from volcanoes, volcanic ash. So this was a volcanic area, and indeed volcanoes were erupting and entombing fossils, as I'll show you shortly. And it seems to be that the acidity of the lake may have contributed to the exceptional preservation, something like bog bodies preserved in peat. It's maybe a similar kind of process. And nearly all the fossils you find, they're often complete. They may be a little scattered like this one, but they nearly always have soft tissues, skin and muscle and feathers or hair and stomach contents and all kinds of other interesting information. I'm only going to talk about the dinosaurs and birds. So here is Sinosauropteryx, which was the first of these feathered dinosaurs to be named. And the bristles, what are they? This was the debate. G&G chickened out, if I can use the expression, said it's a bird. Whereas Chen et al. Were obvious, they recognized, no, we've got to look at the evidence of the skeleton. It is a dinosaur. It is indeed a close relative of Compsognathus, which is also had been described from the same location in Germany where Archaeopteryx comes from. And kind of reconstruction that people made. And in a bit more detail, are they feathers? Well, in the original papers, they called them proto-feathers, just to try and wriggle around and not be too controversial. So what we're looking at in particular is, here's a close-up of the tail. You can see the vertebrae of the tail. And the so-called feather-like structures on each side, they're definitely there. They all look the same, whichever part of the skeleton you look at. They're strips of brownish colored material. The strips are of equal width. And so the critics said they can't be feathers because only birds have got feathers. Whereas I think I was ready to accept from the start, there's no reason that dinosaurs shouldn't have feathers. There's nothing sacrosanct about the idea that feathers originate just from dinosaurs. We know that birds evolved from dinosaurs, therefore you can take feathers down into the dinosaurs. I think the critics didn't accept that. They would not accept that birds evolved from dinosaurs. But it was a tough thing for them to try to explain these structures as something other than simple feathers. Oh, sorry. And so the critics, though, had to fade away as further specimens came to light. So the second of the feathered Chinese dinosaurs was Quadipteryx, named in 1998, a different group. So Sinosauropteryx is a compsognathid, that's one group of flesh-eating dinosaurs. This is an Oviraptorosaur, so that's a different group, different place in the evolutionary tree. And the specimen, again, shows feathers. And what was important about Quadipteryx was that the feathers were not just simple bristles, there were also pennaceous feathers, which are the more complex feathers that we think of with a central quill and branching barbs off the side. And it was very difficult for people to look at these specimens and say, oh, these are shredded skin, because they're actually feathers, they're obviously feathers. And then Microraptor came 2 years later, and these, some of you may remember, these all got big publicity. There's no more publishing these things in China in obscure Chinese journals. These were all in Nature, week after week. And so they really hit the headlines. And Microraptor, yet again, a complete skeleton with feathers. And this one even shows some hint of patterns in the feathers. So sort of stripes or some kind of hint of color, but we don't know what the color would be just from the fossil like that. And the extraordinary thing was this has 4 wings. And calculations showed that it could fly, even though it's a dinosaur. It's not a bird. It's close to birds, but it's not on the line of evolution to birds directly. There were plenty of birds already known. Here's Confucius ornis, and if we thought the Archaeopteryx specimens were amazing, here's a very famous one that's got a supposed male with long tail feathers and a supposed female without. And so this began to show people that these early birds and maybe some of the dinosaurs already were showing certain kinds of complex behavior. But what did this do to our knowledge? Not only then did it give us large numbers of specimens and large numbers of new species, and it showed us that dinosaurs had feathers. It even showed us that some dinosaurs could fly, as well as the ancestors of birds. But it filled up those embarrassing gaps. Remember the diagram I showed you a moment ago with Archaeopteryx and then big gaps. These specimens, both the dinosaurs and the birds, are filling up lots of those gaps of knowledge. And it's important to remember that the feathered dinosaurs belong to many different groups of dinosaurs. They're not just 1 or 2 close to the origin of birds. They're showing you that quite a variety of dinosaurs actually had feathers. And so it's filling up the evolutionary tree, but then that allows us to talk a lot more about functions. So here's a set of diagrams of wings. So it allowed people to begin investigating which of these things could fly and which of them could not. And so it's giving us functional information that fills out our knowledge of the origin of birds. And it also showed us when we plot things like body size against an evolutionary tree, that there was a tremendous phase of miniaturization, which is quite an unusual process to find in a long-term pattern of evolution like this. Because normally in evolution, things just get bigger. And that was the case with dinosaurs, of course. And just to orient you, this is an evolutionary tree of the flesh-eating dinosaurs, the theropods, from the Triassic up to the end of the Cretaceous. So the extinction line is up there. Birds are over here. These are all dinosaurs on the way to birds. And whereas many of them got big, so these yellow spots indicate some of the giants, including T-Rex and some of the other huge predators. So they were doing the normal thing of just getting bigger and bigger and bigger. But this line, getting smaller and smaller. So they start out here at a quarter of a ton, and they end up sort of course, chicken size, like half a kilogram. And that miniaturization was an important part of their evolution towards flight. They were acquiring feathers, perhaps because they needed them. As you get smaller, your need for insulation gets greater, because the risk of heat loss in a small animal is much greater than in a large animal. But also it may be that they were changing their mode of life and perhaps moving into the trees, moving to new diets of feeding on insects or something like that. And so whereas others like T-Rex and so on were just getting big and scary, there was a whole branch of these theropod dinosaurs that were getting smaller and smaller. And that seems to have then culminated in flight, because you can enable yourself to fly either by growing your arms bigger and bigger until they become wings that can support you, or you can start with arms of whatever size they are and just make your body smaller until it's light enough that you can take off. And it seems to have been the miniaturization was more of the process that was going on than simply sprouting bigger wings that would support the body weight. And I'll take that a little further, because in a paper a couple of years ago, Pei, who's a paleontologist in China, looked at a variety of these early dinosaurs with feathers and so on, including Microraptor here, and this ridiculous looking thing called Ichi. That's the shortest dinosaur name if you're looking for pub quiz facts. And it's the weirdest thing. It is feathered, it is a dinosaur, and yet it's also got these kind of bat-like membrane wings. And what Pei and colleagues did was to calculate which of these things could fly. And there's a fairly simple ratio between the area of the wing, because the wing is the structure that holds the creature up. So the area of the wing is in some way proportional to the body mass. And there's a critical threshold where the body mass is light enough that the wing enables the animal to take off and fly. And so in both of these, we're capable of flight. And so that's the first of these biomechanical rules that we can use that work with modern animals. And they have to work with the fossils because, of course, gravity is the same. The nature of biomechanics remains the same. And there's this very well-known ratio between the wing area and the body mass that defines whether you can fly. Simple as that. Aircraft designers know this, and this is important when they're designing aircraft, of course. So it works with everything. So it works today, it obviously works in Cretaceous as well. So this enabled them to discover something we had no idea about, that 4 or 5 lines of dinosaurs, shown in green, were experimenting with flight. And we know that they are doing it in distinctive ways because, for example, these two, the means by which they achieved it are quite different from the means by which birds achieve it. So independently, they have evolved a means of flight. There must have been strong selective pressures that were urging, that were enabling, that were promoting flight. Perhaps then they truly were hunting insects. And if you are able to fly, even if you can glide and just sort of swoop and then land, you can improve your opportunity to capture insects. So this was our paper in 2010. And the title is simple. I think we're not waving a big flag, but we are saying we have determined the color of fossil dinosaurs and birds. And the key word I want you to note, which may not be familiar to some of you, is melanosomes. So this is the key. This is the trick that we were able to do in order to determine color with confidence. And as you'd imagine, of course, this created a great deal of interest and excitement. We were widely reported. This is our dinosaur here, reconstructed as gingery all over. This is Sinosauropteryx with a nice stripy tail. And unknown to us, a rival group were working on colors. They were based at Yale, and both of us had Chinese collaborators. So we were doing it in Bristol, the other group at Yale. And they were working on a Jurassic dinosaur called Anchiornis. And this is their reconstruction, lovely black and white stripy wings and a nice gingery sail on the top of the head. So how did we do it? And what did it mean? So first of all, just to be really clear, we are saying, for example, the upper illustration is definitely wrong. We know that for a fact. And the lower illustration is essentially correct. You might quibble about some details, but the colors, we would argue, and the stripes and that kind of thing are correct. How do we know? We know because of the melanosomes. So this is the secret. In the feathers of living birds, of course, modern birds have a whole variety of colors, and we're only here able to study the melanin pigment. So melanin is a very common pigment in all living things. And in this zebrafinch, for example, it has a variety of colors which are all generated by different forms of melanin. And the two main types are eumelanin and pheomelanin. Eumelanin gives all of these black, brown, and gray colors. Pheomelanin gives ginger. And you might wonder, how can eumelanin, one pigment, give all of those different colors? It's to do with the packing. If to get a black color, you pack the feathers with a huge amount of eumelanin. To get a brown color or even a gray or blonde color, you space it out. You just have in a sense, a more dilute filling. Now, melanin is produced in the skin. It is produced in other organs as well. But before melanin can go into either a hair or a feather, it has to be encapsulated in a structure called a melanosome. And this is what the melanosomes look like. This is the eumelanosome. It's a sort of sausage-shaped structure. This is 1 micron, which is 1/1,000,000th of a meter. So we do the studies using a scanning electron microscope, and this is about the limit of magnification. So this could have been seen by people 20 or 30 years ago, but they didn't. They thought they were bacteria or something else, or just didn't see it. You have to crank the SEM up to the maximum before you can see these things. And so the eumelanosomes are sausage-shaped, and that corresponds to these blacks and browns and grays. And the pheomelanosomes are spherical, ball-shaped, and that corresponds to the ginger. So there you have it. Melanosomes are preserved in the fossils. So we looked at the feathers of Sinosauropteryx. You take a little nip of the feather material off the fossil using a scalpel, put it under the scanning electron microscope, and this is what we saw. So you can see that there are some solid melanosomes. For example, I should use the pointer actually. Some solid melanosomes like here. Most of them are molding. They are molds, negatives of the melanosomes. But they are all circular, spherical. And the fact they're molding is just because the fossil feather, we look at these on slabs. It's like the original specimen. Break it open, they just break through in a random kind of way. And so in many cases, the actual melanosomes, like here, just fall out. So let's refer back to our modern evidence. Which are they most like? These ones, ginger, pheomelanosomes. So what I'm showing you here is what we can call a chain of inference. This is evidence. We have a fossil, we take a sample, we look at it using appropriate instrumentation, we compare back to the modern data, we can identify what it is, and we then declare that this is what Sinosauropteryx looked like. It's all ginger. And the tail is striped because we can see there are tufts of feathers and then blanks and then a tuft and then a blank. And so we would argue this is scientific because it can be disproved. It could be that we just have a chance fossil that happens to in some way preserve this kind of appearance. So a critic, we would say to the critic, well, go and look at a different specimen. You get your own specimen. We won't supervise, you collect it yourself, analyze the thing. Or they might say there's something weird about the scanning electron microscope in Bristol. You faked it up somehow. This is not real. So we'd say, of course, okay, absolutely. You look at it under your SEM and you control that. And equally, they could say, well, maybe you've got it wrong here. This matching of color and shape maybe isn't true. And equally, that would be a way of disproving it. And so the way to disprove it would be to look at lots and lots of modern birds and find if this is a common rule or if it's not always the case. In fact, it always is the case so far. People have not looked at absolutely every feather of all 10,000 species of birds. And maybe someday somebody will find exceptions, and then we'll have to think again, perhaps. More importantly, it's not just birds, because you've probably worked out that if you think of the evolutionary tree, if this feature of melanosomes is unique to birds, that's good, but it doesn't prove that it occurs in their ancestors at all. Let me give you another example. We might say the nightingale sings beautifully, so that kind of song is typical of birds. Therefore, T-Rex had a similar song. You see the lack of logic. But the fact is, this relationship of color and melanosome shape applies also in mammals, in us. And in the evolutionary tree, mammals and birds are at the opposite end of the relationships. So they include between them the dinosaurs and lots of other fossil forms. So we believe that this relationship of melanosome shape and express color is common to all vertebrates. And so any fossil that has feathers or hairs or any similar structure, you can use the method. So it's a big claim, but it could be disproved. So there we are. That's how we do it. It's not assertion or shouting or opinion. Testable. This is science, and you don't need a time machine. Okay, and that's it. So we did the book last year, and Bob Nicholls, his name is there, who is the paleoartist. He lives in Bristol, and we had great fun doing this. And he made his reconstructions. These are digital art, and he has rendered every feather separately, and he's added detail that we didn't have in 2010. For example, the counter shading underneath, the white color underneath, and the banded mask, as it's called, which we were not clear about in 2010. But subsequent study has shown that all Psittacousaurus have this sharp stripe, the banded mask, and so we show that as well. So this is the book, and our attempt then was to present the 10 years of research on paleo color. When we published the paper, of course, we were sticking our necks out. We could have been disproved. We could still be disproved. But since then, hundreds of papers have been published with people looking at different dinosaurs. And we wanted to pluck a few examples and work them into a book. So I'll show you a couple of further stories. So the next one is Psittacosaurus, which is a very different kind of dinosaur. And it's important that we look at a great variety because, of course, Sinosauropteryx is somewhere on the evolutionary line to birds, whereas Psittacosaurus is a long way from that. It's a plant-eating dinosaur. As an adult, bipedal to quadrupedal, maybe quadrupedal as a juvenile, bipedal, quadrupedal as an adult. But the important thing is we're going to show detail of all the color patterns on of the skin and the horns, but also these weird structures on the back, which are actually said to be some sort of a feather. So let's have a closer look. The first thing that's interesting about Psittacosaurus is that many, many juveniles are known, and indeed many nests. And these fossils are very common in China, in Liaoning province. And there's a particular locality in Lujiatun village, and I've been there a few times, and you can see holes where these have been dug out. And at first, when people saw these clutches of apparently, 6, 7, 10 juveniles, they thought these are fakes. They've obviously been glued together with lots of separate specimens. But in fact, there are dozens of these, and I've seen them being excavated. This is what they really look like. And characteristic of these specimens is multiple juveniles, and they're all tending to be facing the same way. So these ones are all facing to the left, the heads are at the left end. And in this case, we wanted to know how old are these. And so my student, Chinese student, Zhao Qi, got permission to section the bones so that he could look at the growth rings in the limb bones. And he was able to establish that all of these were 2 years old, except for number 1 shown in pink, which is 3 years old. So this is big brother or big sister hanging out with the juveniles. But take this further. Why are they all preserved in these clutches? This seems to confirm something that people had thought about dinosaurs for quite a long time. They probably didn't show a great deal of parental care, but the juveniles would stick together in creches or little clusters like this for their own safety. And there's all sorts of reasons that they may not have given parental care. But one of the outcomes, or one key factor, is that dinosaurs were born relatively small. They hatched out of eggs, and those eggs tended to be quite small. They had to grow fast, but they were not protected by parents. And indeed, because they were hatched very small, in certain cases, the babies would have been almost too small for the parents to notice, particularly with the big sauropods. In this case, the parents are not so huge, they're 2 meters long. But that is an unusual feature of the big dinosaurs, at least. The babies might be the size of a kitten, whereas the adult is a 50-ton monster. And it could squash 10 babies with each step. And so there seems to be this crashing. But what's going on here? This has sometimes been called the Chinese Pompeii, because the fossils are preserved in volcanic ash. This is airfall ash, not reworked as in the lake deposits. And it's very clear that the Lujiatun locality is close to an erupting volcano. They're all facing the same way. Almost certainly they have been buried in hot ash falling from the sky. And that has killed them. They've been running away, and hence the Pompeii thing. And here we don't find any feathers or skin or anything, just burnt off. It's like if you've been to Pompeii or seen the images, you've got the skeletons there, and there's often a hollow of the human body where it was, but the flesh has been burnt out. But there is one extraordinary adult specimen that was preserved in the lake deposits, this one here. It's in the Senckenberg Museum in Frankfurt in Germany. And it shows an adult. The head end is there to the right, and the tail, and these extraordinary reed-like feathers on the back. And you can maybe see the skin. So the whole thing is in a kind of bag of skin. And the gut contents in there. So this is a plant eater. So this is a sort of very full intestine, full of plant food, just like what you'd get if you cut open a pig or a sheep or a cow. Their guts are just sort of very bulging with plant material. And so let's have a look at that. We'll just go to and fro between the fossil and the reconstruction. So these were the scientific illustrations that Nicholls did for the paper that was published by Jacob Winter, who's my colleague in Bristol. And in these reconstructions, shown in all directions, Bob Nicholls has been able to use the fossil. So let's just focus on the shoulder region first of all. Look at that sort of speckling over the shoulders. And so here it is in the fossil, speckling the dark patches in that region. And let's have a look behind the leg. You can see the pale color under the bottom area and the back of the leg, and then kind of speckling. I should have been using the pointer. I do apologize. I'm not quite sure if I can re-establish this. Thank you. Oh, you can just hold that, Stuart. Thank you. Sorry about that. I won't touch it again. I promise. I'll use this thing. Okay. So we'll just flip back then, having looked at the back of the leg and the underside. And you can see you've been able to use that pale color on the underside. Oh, use the pointer. Pale color on the underside, and the sort of speckling, and then the darker color, etc., etc. So there we are. We've got all the color in a less feathered dinosaur. And that's the reconstruction that he did with the babies, the adult. And there's even color evidence on the cloaca, the bottom opening. This is a polite audience, so I won't say any more about that, but whether they flash their bottoms at each other, who knows? Baboon-like, something like that. Let's look at another group altogether. Those are both dinosaurs, but we can widen the field to include pterosaurs, the flying reptiles. These are not dinosaurs, they're cousins of dinosaurs. And it's long, so they've been studied a lot, everybody's familiar with them. There are many, many species, large and small, and they've long been known to have some sort of insulating structures, which have been called pycnofibers as a sort of non-controversial term. Mammals have got hair, birds have got feathers, pterosaurs have got pycnofibers. And these were discovered in the 1840s. People have known that pterosaurs were insulated for a long time. And the argument was sort of logical. These things can fly, just like birds. They must have had a very high metabolic rate. That means they consume a lot of oxygen, high body temperature, very active mode of life. Having some kind of insulation, pycnofibers, hair, feathers, whatever, having some kind of insulation is what you expect. So we studied some specimens from the early Jurassic of Anurognathids, that's a particular group of pterosaurs, and we discovered they got feathers. So here we go. This is our 2018 paper where we announced that they have integumentary structures with complex feather-like branching. And that was a bit of a shocker at the time. The pterosaur community were furious, but the evidence seemed to us rather clear. They have simple structures, which is what people expected, but they also have structures that branch at the end and branch halfway down, and indeed branch at the base. And all four of these simple feather types are known in birds and in dinosaurs. So our argument was, we're not just talking about one simple whiskery thing where you might be able to say, well, who knows what it is? We don't know. But the fact that they have at least these four structures, we said, suggests they're probably simply feathers. These are dinosaur cousins, so they're not that far from dinosaurs. And here's the reconstruction by Bob Nicholls, a very happy looking Anurognathed. They're insect eaters, I should say. And you can see why this one looks happy. It's just spotted a nice juicy lacewing. And let's look at another pterosaur, Tupandactylus. This is one of the Cretaceous ones, which, whereas Anurognathed is not too huge, it's probably the size of a pigeon. This thing is vast. I think it had a wingspan of about 5 meters. 16, 17 feet, and the most ridiculous head structure. So if I tell you that's the eye, and the little circular structure marks that, then you can maybe work out this is the mouth, and God knows what that is, or that. And the body is here, here are the arms, the wings, and the hind limbs, and so on. So what on earth is this ridiculously huge head? And it's not fanciful. Here's one of the fossils, and in close up, the fossil, these structures are not scratch marks by the preparator. This is actually preserved skin spanning between these two struts or spars. It's like a sail on a yacht. And it's sufficiently thick, the skin, that it's been preserved, and the organic material within it has been preserved as well. Sufficient to allow people to reconstruct the patterns that different species have different shapes of head structures, with different patterns on them, different patterns of dots, and some maybe even photoluminescence being suggested. So here's our reconstruction of Tupandactylus, and after the book was published in a paper in Nature earlier this year, a different group of researchers, not including us, noted that in the skin they could identify melanosomes and feathers, and so they confirmed our 2018 paper. The final story is about a large armored dinosaur from the early Cretaceous of Canada. So this is to stress that not all from China. I should have said Tupandactylus is from Brazil. So we've seen several Chinese specimens. We've seen one from Brazil. This is from Canada. And the Athabasca tar sands are sands that are full of tar. One of the pleasures of geology is some of the terminology is quite straightforward. And here we have the mining operations. It's in the north of Alberta, covered in snow much of the time. And these are giant trucks, these little spots here. So this really rips up the landscape. And a number of years ago, then, a rare dinosaur skeleton was found, excavated by Don Henderson, who's the curator of dinosaurs at the Terrell Museum, one of my former PhD students. And here it is. So there's a little person up here. So this is a pretty big thing. It was called Borealopelta, which means somewhere northern armored thing. And what we're looking at is the head is at this end. This is an ankylosaur, which are the armored plant-eating dinosaurs, as big as a tank and massively armored. So the head and the neck region are completely covered in armor plates, and the body as well. Oops, sorry, the body, a great mesh of plates over the back. And around the neck and the shoulders are great scimitar-like plates. We'll see that in a moment. And so this was published in 2017. And in that paper, Brown and colleagues noted or found that not only do they have the bony plates preserved, but there's also the horny covering, the keratin covering over the whole body, containing pheomelanin, so a gingery colored pigment in the horn covering of these plates. And so here's our reconstruction. And to give you the scale, these plates are behind the shoulders are 1 meter, 1 yard in length. And so Boudica, look out. This thing was a humble plant eater. It probably weighed 10 or 15 tons. It would have been preyed on by things like T-Rex, which would have been trying to turn it over to get at the belly. But it would hunker down for protection. But also, of course, with these rather sharp-edged blades, it could cause quite a lot of damage, I think, as well. But the fact is, we know they were gingery color, which was a bit unexpected. So I just want to wrap this up and go reiterate the themes I mentioned at the start. I've told the story of color. So this, in a sense, was the hardest thing to do. What color were dinosaurs? We know what colors they were. Not all dinosaurs, but those where we have these kinds of exceptional fossils. So one of the big things we worship, not worship, that we glorify or that we rely on are exceptional fossils. And I've shown you a few. And they will continue to be found, and we will continue to find interesting things in them. Number two is the same biological rules applied today and in the past. So that's not unexpected. And that is the basis of that sort of scientific approach. This always works today, therefore, why should it not work in the Jurassic? And I think nobody has yet found a reason to truly say why gravity would be different in the Jurassic, or why the Earth would operate in a totally different way, or why the bones of the skeleton of fossil creatures would have different characteristics than the bones of modern creatures. In some cases, we can even do multiple tests. So let's show you a couple of quick examples. And we do now know these things about dinosaurs. So this has all changed in the last 25 years or so. Side by side with discoveries of all these amazing fossils from China, as well as the move of much of paleobiology into the realm of testable science. Color, speed, bite force, feeding, growth rates, all known, all testable. And multiply. I'm sorry, the equation's gone off the side, doesn't matter. You can use trackways, of course, as many of you know, to calculate running speed, because the faster you run, the further apart your footprints, if you think about walking, running. So for any individual, speed is proportional to the stride length. That's simple, that's a fact. How do we do it for multiple species? You have a formula that factors in the size, the body size. And you factor in the body size simply by measuring the length of the leg. And so speed, so just to repeat that briefly, speed is proportional to stride length for any individual organism. So for an ostrich, there is a particular way of calculating. For a human, for a horse, for a dog. But there is a general formula here which takes account of leg length, and therefore you can calculate speed. How do we know it works for the Jurassic? It always works in the present day. Whether you're looking at a biped like an ostrich or a human, or a quadruped like a horse or a dog, it always works. Therefore, it works in the past. But you can also calculate maximum running speeds from proportions of the limbs. And so if you think of the human case, fast running humans tend to have more muscular legs. And it's the size of those muscles, particularly sprinters. I'm not thinking of long distance runners who tend to be thin and so on. But sprinters have highly muscular legs. And the diameter of the leg and those leg muscles is proportional to the speed they can achieve. And so John Hutchinson of the Royal Veterinary College used that relationship to calculate, could a chicken weighing 6 tons still be a sprinter? So we know that a chicken weighing ½ a kilogram is a bit of a sprinter. You may not realize that, but if you try to catch a live chicken, they run very fast. And the point is, no, it could not, because it can do that sprinting at small size, but at large size, the 6-ton chicken is up there, and fast running, any kind of running is impossible. fast running is only really possible for these very lightweight creatures. But what Hutchinson was able to calculate was the running speed of T-Rex, 27 kilometers per hour, which agrees with the speed calculated from trackways. And so we tested twice. Each way is defensible, and they both agree. And one more example for bite force. That can be calculated from fossil specimens. So here's a piece of Triceratops bone that has been bitten by a T-Rex, and the depth to which the tooth has gone can be calculated by the force can be calculated by physical experiments. What force is needed to drive a tooth in 3 centimeters into the bone? So you can do it by sort of force plate experiments, classical mechanics type physical experiments, or you can do the calculation using 3D digital models. And so this is a scanned skull of T-Rex with the muscles reconstructed, the red lines, the food items in yellow, and then mapping on the physical properties of the muscles and the bone. The bite force was calculated at the top there, 35 to 57,000 newtons. Whereas the human range, notice, is just a paltry few hundred newtons. And even the great white shark, which has the biggest bite force of any living animal, falls a lot short of T-Rex. Why do we believe that these physical computational models work? The fact is that the paleontologists like Professor Emily Rayfield here at Bristol use standard methods that are used in engineering. Finite element analysis has been used for many decades as a standard tool in designing buildings and aircraft and bridges and things like that. And the reason people use it is that you can make a complex 3-dimensional structure in the computer, make your model, and you can then give it the physical properties of whatever you intend to build the thing from. So, for example, steel or aluminium or a mix of concrete and steel, depending on what the structure will be. And you test it using finite element analysis to work out how you're going to construct the thing. That's very different from the medieval approach, of course, which was just to pile up lots of bricks and hope that if it fell down, start again. And that's how our churches were built. But now we don't do it that way. And so if you've been on an aircraft, you trust that FEA works. I don't think they ever ask you as you walk on, do you believe in engineering? Do you trust all of that? But you do. And so this is what Emily did with T-Rex, and the heat maps at the bottom are showing the forces. The red color indicates high stress, blue color, low stress. And so once you've made her model and meshed it, the second figure, then added material properties of dense bone and open bone and the teeth and all the different portions have different material properties. She can twist and turn and test the bite forces and work out how the skull would operate. And the great thing here is your skull in the computer has got the properties of bone. Whereas if you made a plastic model or a metal model, that would be pointless because it would not have the properties of bone. Anyway, so those are the 3 themes, I think. We can find out quite a lot about dinosaurs now based on the application of appropriate scientific methods. Many of you will be familiar with the term uniformitarianism. So this was given to us in the 1830s by early geologists like Charles Lyell, who said the understanding of the past is informed by our knowledge of the laws of nature today. We don't assume any miraculous aspects of the Earth in the past. That the importance of all these new fossils from China has been huge. And I think also a final point, which I didn't mention, but for younger persons, it's been fantastically invigorating that we've been able to collaborate worldwide on a lot of this work in ways that when I started in the trade, we would have thought wouldn't be possible, that you can go to China in normal times and collaborate and get access to amazing stuff. And that makes the business of being a scientist a great thing, that you get to work with lots of other people. So I'll stop there. Thank you.